So yeah, hi everyone. Welcome to Multimodal Weekly. This is a webinar series hosted by the team at 12 Labs, and we've been meeting on a weekly basis over the past 2 years or so. Some of you, regular attendees. Some of you are pretty new, but essentially, here are some of the topics that we tend to cover on a weekly basis: news research in multimodal AI and foundation models, innovative application in multimodal different verticals. We have a pretty active community. Discord where members share their relevant projects around like multimodal and video understanding. And oftentimes we have internal team members talk about how to use our platform and API. Here's some sample, some of the most recent session of Multimodal Weekly. We have researchers working, at different, topics ranging from, streaming on live to, benchmarking the understanding to, video captioning to, mixture of expert modality combination, etc. For today's session, we'll have Pietro Mazzaglia, currently a senior machine learning researcher at Qualcomm, and super excited to have him talk about one of his recent work called learning generalist agents using multimodal foundation world models. Just a brief, abstract about this work. Essentially, it overcome a lot of the problems between applying reinforcement learning into, multimodal vision language model. So he presented multimodal foundation world models that can connect and align the representation of foundation VLMs with the latent space of generative world models for reinforcement learning without any language annotation. And the resulting agent learning framework is called GenRL that allows ones to specify tasks through vision or language prompt, ground them in the embodied domain dynamics, and learn the corresponding behaviors in imagination. So yeah, super excited to have Pietro join and talk more about his work. Thanks for joining again. I think you're based in Amsterdam, right? So thanks for joining later in the afternoon. And for the attendees, yeah, feel free to send your question on the Zoom chat, and we'll have a very short Q&A session after Pietro finished. So with that, I will stop sharing my screen, and yeah, Pietro, feel free to unmute yourself and share your screen and start your presentation.
Yeah, so yeah, hi James, thank you very much for having me today. And yeah, let me start sharing my screen so we can get started. All right. All right, so as James already introduced, today we're talking about GenRL or General. Personally, I prefer the latter, but everyone pronounces it differently. So it's called Multimodal-Foundation World Models for Generalization in Embodied Agents. And this was actually the last work of my PhD at Ghent University, and a collaboration with the Mila Institute in Canada and ServiceNow Research. So we start from the premise that foundation models are generalist, in the sense that in recent years, we have seen people collecting huge data sets of like images, text, speech, videos, and training very, very large neural models that are called foundation model, in that they contain knowledge about a lot of concepts in our world. And these models are generalist in the sense that they can easily be applied to many tasks. Like a lot of times these days, even if you're not sure if the model is able to perform a certain task, I feel like 80-90% of the time they will be able to answer to your question, even though they're not specifically trained for a certain task. So they're really generalist, and they can perform a variety of tasks like following instruction, captioning images, performing translation, and so on. But what about embodied domains? Like, for instance, robotics. Robotics is, in general, embodied domains are much harder to deal with, because the representation we're dealing with is not anymore just language, but it's actually actions in the real world. So we have to deal with real interactions that have an effect on our environment. And training a foundation model in these embodied domains is, in a way, harder Because first of all, we can have variety of morphologies, like we saw manipulation robots, or we can have multiple-legged robot. Like these days, we also have humanoid robots, for instance. There is a problem of safety and cost because these robots, or for instance, if we're talking autonomous riding cars, they have a cost. They're not just a model that you run on a GPU. You need that, but you also need the actual hardware to perform the action in the real environment. And of course, they can be unsafe. Like they can actually harm you or things in the environment if not used wisely. And finally, the data collection requires a lot of human supervision. You cannot just scrape the internet and find data, but you actually have to be there and supervise your robot, or for instance, using VR to perform operations with the robot and similar settings. So it actually requires a lot of human supervision. So the question we asked ourselves for this work was, how can we leverage foundation models for generalization in embodied domains? And what we came out is GenRL or GenRL, and is this framework that allows to go from visual and language inputs to interactive embodied agents. Like for instance, you can ask to open the oven, or you can show a video of a person walking, or you can ask the spider of the simulator to crawl, or you can show a dog hopping, trotting in the grass, and the model is able to handle the prompt and to actually enable an agent to perform such actions in the environment. But how does GenRL work? So GenRL is made of two main components. One is the multimodal representation learning for decision making, and the other is the reinforcement learning part from multimodal prompts. Let's start talking about how we do the multimodal representation learning, which combines a generative word model and a foundation visual language model through a mechanism that we call connecting and aligning. So our multimodal foundation word model is made of these two components. First of all, we have the generative word model. This can be seen as some form of sequential autoencoder. So the model takes the encoder, takes some observation from the environment, so some images in, like the images of the kitchen. Then there is a sequential model that can also take in actions and previous states of the environment, latent states, and then it can predict the future, for instance, like future steps. And it can also reconstruct from these latent states the observation from the environment again. So basically, the model can both predict the future given certain actions in this latent state, that is S, or it can take S and decode it to actual observation back in the environment visualization. So perform reconstruction like a typical autoencoder. And so just to give you some example, presentation went further. So just to give you some example of predictions of the word model, if we just take the Walker environment and we provide a sequence of random actions, we can see that the model, which we see here at the bottom, is actually able to predict what are the effects of this action. Of course, it's not completely loyal to reality because these are just the model guess of what is going to happen, but you can see that the images, at least at this resolution, they're kind of crisp, and the actions of the agents, they're actually kind of like they stick to reality for a good amount of time. So after we have this model, we can actually use it, for instance, for planning. So we can ask the model what's going to happen if we give some actions and we perform in the environment, and it can tell us what the future is going to look like. The other part of the which is the multimodal part of the framework, is the multimodal foundation model. And in our case, specifically, we focus on this clip-like model, which take language or visual inputs, and they are able to project them into this smaller space, this embedding space, made of language embeddings and visual embeddings, where the same kind of action, so for instance, like the language embedding for running and the visual embedding for running, they should be mapped kind of close. So like different visual embedding and different language embedding should be apart, while the same corresponding language and visual part should be close in this embedding space. So they have, normally we say they have a high cosine similarity. So how can we leverage the knowledge from both representations? So we perform two steps. So the first step is connecting. So we have this neural model. It's a sequential model. It's called the connector. This model is trained to take embedding from the visual language model. So embedding observation from the environment. Let's say here we see the kitchen environment. We take a sequence of observation, we embed them. So we take the video, we embed it, and then we ask the connectors to predict the corresponding sequence of word model states. So we take the word model states that we took from the word model, and we ask this connector to predict them from the embedding. And this allows us to go from visual embedding to word model states. And at the same time, it generally allows us to ground videos in the embodied domain. Because since visual embedding of the same actions will be mapped kind of close in the embedding space of the multimodal foundation models, if we just provide the same kind of action, but in a different domain, then it will be still mapped to the same kind of actions, but in the domain that the word model knows. So we can actually go from like these video prompts to predictions of what they're going to look like in the environment. As I said, this part works very well for the visual part. And this is because if we look at the embedding representations, we can see this as an hypersphere where the points that are close to the visual embedding, which are the same actions, but like in different domains, they're mapped in a close by area. So when we feed this to the connector, they will still be decoded into the same states and as the one with the domain, with the embodied domain. So what happens when we provide instead language embedding? So if we look into the clip representation, this language embedding, they are close to the visual embedding, but they're still far apart enough in a way that the model is not able to transfer directly from a language embedding of, let's say, the agent running to the actual word model states. So what we thought first was like, hey, we can just add some noise on the visual embedding during training so that we make this area wider. So that like embedding that are close, but like a bit more far apart, they will still be mapped to the same actions in the embodied domain. And this works, but of course it also affects the performance of the connector, because if we train the connector with noise, the word model states prediction, they will be, of course, of lower quality. And we don't want to get to do that. So what we came out in the end is this aligner network, which is an additional network that takes some visual embedding with noise and learns them to denoise them back to the original embedding. So this aligner at inference time allows us to do the same with language embedding, which are somehow similar to like a noisy version of the visual embedding. So we feed the language embedding, we ask the aligner, what is the closest visual embedding to this language embedding, and it would be mapped back to the visual embedding space. And by doing this, we're also able to ground language in the embodied domain. So now we can take some actual language prompt, feed them to the aligner first, transform it into this common embedding space, and then feed them again through the connector, and we can get the word model states that actually look like this, for instance, in this sticker environment. So this was the multimodal representation learning part of the word model. Now we actually have to turn these representations, so these word model states, into actual action. And for this, we use reinforcement learning from multimodal prompts. So how do we go from like a multimodal prompt, which can be indeed an image, a video, or language, to a reward? So what we do is that we first embed this prompt, which getting this embedding from the foundation model. So we take the language prompt or the vision prompt, we feed it through the multimodal foundation model, we get the corresponding embedding, and then we put this through the connector, and this way we obtain the word model states that correspond to the task. Since we have this, now we can provide some actions to the word model, predict what the actions, what the state after the actions of the agent will look like, and we can compare this agent, the states reached by the agent, with the state that correspond to the task. By performing some simple cosine distance, like computing this cosine distance between the two, we can use this as a reward for reinforcement learning. So we can train an actor critic, which is typical reinforcement learning, to perform the actions that the user input through the prompt. So how does GenRL actually perform in the environment? So first, I will explain our training setting because it's in a way kind of unique because this work it was back then, but I mean, I think it still is a bit different from the usual reinforcement learning setting. So we want to assess generalization performance of the agent. So what we want is that we train on a certain set of tasks, and we want from like a new prompt, which can be visual or language, the agent to generalize to a new kind of task. So we collect a data set that contains both structured data, so some in-distribution task that we take from the replay buffer on an expert agent. So we run an expert agent, we collect, let's say, some walking or running behaviors, and we put them in the data set. And then in order to drive generalization, we also add some unstructured data, so some exploration data in the environment. And this is done in order to make the distribution wider. Otherwise, the agent will always be able to learn only the task that the expert knows. So instead, we want like more wide distribution. Then we evaluate the agent zero shot. So we provide no rewards to the agent. We just train it with the GenRL framework. And then we use handcrafted reward as a proxy for performance. So we actually use reward only to evaluate how well the agent is doing. So let's see the first setting, which is the language to action in distribution. So big table here. We see lots of tasks on the left in different domains. We have the walker, we have the stickman, we have the quadruped, the cheetah, and the kitchen environment. And on the right, we see multiple baselines. So we have general, and we also have many baselines which compute rewards using the foundation model, but just using the cosine similarity between observation in the environment and the prompt from the user. And they use this cosine simulator as a reward. While instead, as I stated before, we actually use the distance inside the world model state. So we first ground the world model representation, and then we use the distance between world model states that correspond to the task and the agent world model state as a reward. And then we use model-based RL for optimization. So we see here that compared to the baselines, they don't learn a multimodal foundation world model. GenRL performs best in almost all the environment. There are some environments in the kitchen case where other approaches perform well, but it's mostly like more static tasks like turning on the light or turning on the kitchen burner. But instead we see that like on very dynamic tasks like running or walking, GenRL actually perform better. Then we evaluate on a new set of tasks, which we don't have a description here because it's a very large set. It's 21 tasks, but for each task, we provide a different kind of prompt. And this can be some of the prompt that we saw before, like for instance, like doing the splits, or it can be like jumping, it can be like doing a backflip. And we evaluate all the approaches that we saw before. And we see that in terms of generalization, also general is the approach that performs best, followed by this WM clip approach, which is model-based, but it doesn't use a multimodal foundation world model. Then let's have a look at some video to action generalization. So here we want to see how the agents perform when, instead of providing a language prompt, we provide a video as a prompt. The video we see here, and as we observe, they have very different cameras from the typical environment where we benchmark the agent on. And they also have very different visual appearance. Like for instance, the spider is just a drawing of a spider walking. The dog, it looks completely different from the cheetah robot, but it still shows the trotting of the agent. So in all these cases, we again see that GenRL is overall the agent that performs best in terms of generalization from video prompt. Finally, I thought this was an interesting ablation to show is which data is important for generalization. And as I was telling before, we have multiple data sets in the general replay buffer, and of course for all the other approaches too. But like we see that for general, in order to perform more difficult tasks like running and walking, you actually need the expert data about that task or a very similar task in order to perform as well. So for instance, if you want to be able to run, we see that just training on the running data set is the solution that works the best. Or if you want to walk, we see that having running or walking data is necessary in order for the agent to perform well. While, for instance, standing, which is a very narrow distribution indeed, it doesn't help almost anywhere. Like even on the standing task, it's not that helpful to just have standing data because it doesn't make the agent robust to just see the agent standing. And overall, we see the exploration data and in general, combining all the data together is very helpful. So the scaling performance of general are also good. Like more data will help improving performance overall. So that was it about the project. Thank you very much, and I look forward to any question. And the paper is there, the code is open source, and we also have data set and models. So
Awesome. Thanks a lot, Pietro. Let's see if there's any question. Oops. Yeah, I think there's a question in the chat. Can you see it? Can GenRL provide interpretable action rationales or visual language routing feedback when asked for specific action?
yeah, so I think that's actually a very good question. So general can provide uninterpretable action rationales. Yes, I would say so. The reconstruction that we see, for instance, here from the agent, like the video that we see here on the right, in this case from language, but also in this other case from video prompt, they provide a reconstruction in visual space in the environment of what the agent understands about the user prompt. So in terms of providing an interpretable action rationale, I think that's actually one of the big strengths of this framework, because you can, before actually training an agent to perform such actions, you can see, okay, the agent understood the prompt and is going to do the action as I wanted. About the specific actions, that's actually it's a complicated part of the framework, because in order to generalize, we had to add noise. So for instance, you can ask multiple kind of tasks, but asking specific prompt, like for instance, walking slowly or walking with like a specific style, can be harder for the model to understand, mostly because in order to do this alignment part, we had to add noise into the model. And that, of course, allows to understand the language part, but also like it makes it harder to understand complicated prompts. So that's actually one part that it would be interesting to improve for future work.
Yep.
Yeah.
Cool. Yeah, so now got another question. How does GenRL compare with NVIDIA GR00T N1?
Yeah, so if I'm not mistaken, I think NVIDIA GR00T N1 is one of the latest visual language action model for humanoids, probably, if it's the latest one. And I personally don't remember all the detail about this model. I know that it learns to directly map language to actions. For instance, I don't know if it does allow to map videos to actions. That's one thing that I don't think NVIDIA GR00T N1. At the same time, there's also the fact that NVIDIA GR00T N1 is probably trained on a lot of language annotations. That means that, and that's a very time constraining process, like you have to stay there and annotate for each task what you're doing. Well, here, what instead we do is that we just collect a lot of data, and then the model kind of like automatically labels the data, because the clip model already knows how to project the visual part in the embedding space, and then through the alignment, we kind of like get the language part for free. So we don't have to train on language. We just perform this connection alignment process, and we get rid of needing language annotation. And I think that's one of the benefits. At the same time, I think that probably, yeah, if you really want to perform like very accurate action, like humanoid manipulation, probably NVIDIA Gluten one will be better in that case, because it's actually trained to perform those actions very accurately and with a lot of demonstration and annotation. So in that sense, it can be. But I feel like General, indeed, we didn't push the boundaries of General to that point yet.
Okay. And then Swati have a follow-up question. How does GenRL mitigate overfitting to visual language priors from pre-trained VLMs when operating in environments with our distribution dynamics?
Yeah, so I'm not sure I fully understand the question, but I think the question is related to transferring to different dynamics. Like, for instance, we train on the walker dynamics, and then we want to use the same word model on the humanoid environment or like the cheetah environment. At the current state, we did not analyze this transfer setting. So the generalization is to multiple task and multimodality, but is not to a different dynamics. So the dynamics of the environment is assumed to stay the same. You just provide new tasks and new prompts in different modalities, and that's where the agent generalize. But I feel like we train very small models. Like I think these were like in the order of 40 million parameters. I feel like if you want to scale up to multiple dynamics and visual dynamics, you actually need a much larger model. That's also something to consider.
Okay. Yeah, I think that's pretty much all the question that we have here. Minas, I think he already left, but got a praise at excellent work presentation. Thank you very much, Pietro. Looking forward to your follow-up work. And maybe we just follow up with that. Like, are you working on any exciting research project right now at Qualcomm? Anything that you would like to share before we end?
Sure. I mean, I'm working in the robotics team at Qualcomm right now. I think in general, multimodality and this kind of like vision language action model are definitely interesting for us. I cannot tell more, but like I'm actually working on some stuff right now for some submissions. So please stay tuned, and some work will be out soon about similar concept.
Absolutely. Perfect. Well, thanks again, Pietro, for spending the time talking about GenRL today. Really exciting work that combining, multimodal understanding with the word reinforcement learning, vision language action. I think that's definitely like how the next frontier, like physical AI and world models, those kind of things are training to works. So excited to see more and more research, I guess the research ideas and innovation happening in this space over the next couple of months. And the recording of this session will be available on YouTube probably in the next couple of days. So be sure to share that on the 12 Apps channel. And for those of you who are attending, thanks again for spending time quickly walking over the talk with Pietro. And yeah, if you find this interesting, we'd love to have you come back in the next few weeks for more research talk. Awesome. Thanks, everyone. Thanks, Pietro, and hope you have a good rest of your weekend.
Yeah, thank you so much. Thank you so much for having me, and thank you so much for the interesting question. Have a good one.